Foundation Models for Embodied Decision-Making Agents, Part 16. I want to discuss a talk by Ken Goldberg, professor, UC Berkeley. He gave a talk that kind of was talking about end-to-end versus engineering. So machine learning systems, AI, from the perspective of the researcher and the engineer, whether we have pure data-driven end-to-end learning, or whether we can use priors or engineering to help the machine learn a little bit faster. Within that context, I want to talk about two papers. One is the MOKA paper, and the other is Hu et al. They both look at large language models and visual language models as a sort of bridge between general intelligence that is available now in the large language model space and robotics. I think these things are related because fundamentally we can ask ourselves the question, can you learn something, you being the agent, can you learn something from just pure data? So can you learn something from just observing the world and iterating many times, or should you have some priors that help you understand the world? For example, would it be helpful to have a physics formula like one of the presentations I discussed a little bit earlier, Atasanov, professor at something like that, I might be butchering his name, professor at UC San Diego, who is using physics priors such as Hamiltonian energy functions to model the robot. We could use the same thing for the environment. Can we have a representation of the environment which helps reduce the search space? So this is generally what this talk was about. But I think, like any good scientist, I think what Ken does, he makes me think, he makes me work. That's the best compliment I can give to anybody who gives a presentation that I attend, right? You made me work, you made me think. So whether what he said is really breakthrough knowledge, whether I should be jumping on that bandwagon or whether I should be opposed to it, is really not that relevant. I think what matters to me is that I was inspired to think about a couple of things, and those are the things I want to talk about it here. So let me start with Ken's central argument, and then talk about the MOKA paper, and then talk about the Hu paper, which are related. So Ken's central argument is that we need some old-fashioned engineering. It's not just about data. Take, for example, robotics in the surgery space, which is something Ken's working on. I'm familiar with that also through my brother. There's a company here at Stanford, Intuitive Surgical, which is working on those things. So, so what they're doing is really teaching the robot dexterity. They're doing a lot of other things too, but that's the one thing that the robot absolutely has to learn, dexterity, because you're dealing with very fine-grained finger motions, which is what a surgeon is doing. The way they learn how to do surgery is they have video data, which they log, and then they learn from that, and they understand how a specific action takes place, and then they can do that basically through robotics. I think there's some teleoperation also involved there, but in general, that's how it works. So the question here is, well, you could, in principle, have a video representation, or you could shoot videos of operations. You can represent that in virtual world, and then have the robot train in simulation, millions of operations, and therefore, learn how to do operations. Do you need some prior knowledge? Do you need to understand what a tissue is? Do you need to understand that a liver tissue is different than this tissue or that tissue? Do you need to understand that you can't poke an artery while they're doing surgery? All these things that a surgeon is learning through years and years of painstaking work Do you really need to understand those things, or can you just learn in simulation? So again, can we just have data and observations and imitation, and then maybe some form of reinforcement learning that is applied, like Sergey Levin says in one of his talks, you have a representation of what's possible. So this is the real world as we know it, let's say, as expressed in a visual language model. This is what the MOKA people are doing, and what Hu and all are doing. So you represent the world. Let's say you represent the world. You take pictures of the world, and then you run a transformer architecture on that, which is you try to understand all the relationships between all the the components of the which are in the picture, but then you use some sort of reinforcement learning maybe to find the best trajectory. To paraphrase from the MOKA paper, since robust grasping relies on contact physics and gripper design, which is beyond the capability of existing pre-trained VLMs, so which means that existing pre-trained VLMs don't understand physics. They have a representation of visuals, and that's why they work really well for navigation. That's why they work really well for something like, let's say, an occupancy network. You can use visual language model, or just visual transformers in general. You can use visual transformers for navigation, because what you really care about, more or less, is like the word says, occupancy. You don't need to understand how a certain object feels. You don't need to understand what it means to penetrate a certain tissue. You don't need to understand what it feels like to poke an artery. So when it's just about navigation, physics and touch and texture and material consistency don't matter as much. So in the MOKA paper, which came out of Berkeley, what they're doing is they're using visual language models to guide a robot for grasping, but they're not interested in grasping in terms of whether you're grasping a metal or a porcelain or an egg. All they care about is to grasp the thing at the right place. The way they're doing this is they're using so-called affordance points or key points, and then waypoints. What that means is you look at, let's say, a spatula, or you look at a shovel, and you have a visual language model which takes the shovel's image and then has a representation. This is a shovel. And then you can have a large language model querying the visual language model. Well, how long is the shovel? Okay, where do you think I could best grasp it? Well, you should start here, and then hold it there, and then lift it up. Maybe we can learn something about center of mass. Maybe we can use a transformer which has a little bit more general knowledge, and then through reinforcement learning, understand a little bit better how to actually grasp that thing, which is kind of where this paper is going, the MOKA paper. It's an interactive design between language and vision. So I see something and I want to do something, for example, grasp a spatula, and then I interactively ask, or I generate, well, you should touch it here, and then you should lift it up, and you should move it over there. So those are the kinds of basic things that the MOKA paper is discussing. Hu is going a little bit deeper, because the difference between MOKA and Hu is, in the Hu case, they have a representation in pictures, and then with language they want to generate actions. The problem with the Hu paper is that each action has to be trained. So how to actually grasp a spatula, that has to be trained. And in the MOKA paper, that is generalizable. So you don't need to pre-train how to grasp the spatula. You can have those affordance points, and that's enough for the system to understand where to grasp and how to move that thing around. Now, of course, there's a lot more depth and engineering and subtlety to it, but for our purposes here, I think where we wanna concentrate the conversation on is really on Ken's fundamental question. Okay, end-to-end data? Is data all we need, or is there some old-fashioned engineering required? And I think the answer is yes, we can use some old-fashioned engineering to reduce the search space, increase the speed of, let's say, understanding, things like that. But overall, I think we're always better off having less priors and understanding the world through trial and error. And the reason for that is, and this is the third thing I want to add here, which is actually a conversation that I also attended just by sheer coincidence on the same day, which is a presentation by Christopher Peacock, and he's a philosopher at Columbia, and he was talking about the a priori in metaphysics, so in philosophy. So basically, is there such a thing as a priori knowledge, and which is knowledge that exists without our experience, right? So there is knowledge that we have, we humans, physics, chemistry, anecdotal knowledge, wisdom, all that kind of stuff, math. But then there is also this idea that maybe there is a knowledge or some sort of knowledge out there that is out there without us really having agency, an a priori knowledge. And I would say that robotics is a fantastic avenue to research this question, because we can actually test that. We can have a car trained end to end, like a Tesla, that is literally not being fed any kind of physics priors. Hence, the car still understands physics. It knows how to avoid objects. It knows how to slow down, how to speed up, how to take a curve. It does the differential equations necessary to do a curve without having those differential equations in the model. So the question arises, and the same could be asked for GPT. I mean, does GPT understand the English language? Well, it's able to write poetry. Maybe it's not very good, but it's able to do it. So does it understand the English language? So the question of understanding and the question of a priori and the question of knowledge, in my opinion, are being tested here with the evolution of robotics. And my answer is yes, there is an a priori. Very simple. For example, a move 37 by AlphaGo 0, or what Davide Scaramuzza has shown with his drones, which is a move that humans would not have come up with. And that's in the physical world, right? So this is something that happens with Davide, was in the physical world. And I'm pretty sure if we have the proper training methods for a self-driving car, we will get to the point where cars will do things that are superhuman, in a sense that they are something humans would never have done. Let's say the way they go from A to B, the way they avoid obstacles, they will come up with, because, and this is now another presentation I want to add here, which is Sergey Levin and his presentation about big data, offline reinforcement learning. Now, that presentation actually warrants its own discussion. So I'm going to talk about this in a separate presentation, but I want to mention it here because there's one episode in this paper that I think encompasses this conversation really well, which is, look, we have the ability to represent the world in a compact, machine understandable way, which is large language models, video language models, offline reinforcement learning. So there's a couple of things where we can have good machine readable representation of real events. And what that means is that we kind of have a representation of what's possible, at least to our knowledge, what's possible. We can observe that. That's observable, right? We can just look at what's possible. That's what experiments are about. So we look out there, we look at what's possible, and then we have, with specific, particularly reinforcement learning inspired algorithms. It doesn't have to be, but this is sort of the state of the art in terms of finding the best trajectory. So imagine a car that is really good. So you have data about a driver that is very good on a highway, You have data about a driver that's very good in parking, and you have data about a driver that is very good at backing up and very good at dense traffic. And the beauty of reinforcement learning is that it learns the optimal trajectory from all of these and finds the best optimal trajectory and from what's possible. So that's kind of what offline reinforcement learning is. And I think we're still stuck in this philosophical realm of, well, there's really, you can say there is an a priori, but there really isn't, because we can only learn from what we can observe. So we can't prove that there is an a priori, because even our best AI can only learn from what's observable. Yes, but at least we can find trajectories that are superhuman. And in that sense, there must be an a priori, because there is knowledge to be acquired that we don't know yet. And that goes into Gödel, right? Gödel kind of said that. How is it possible that we generate knowledge from axioms that are not related to those axioms? In other words, like if there is an a priori, if there is a way to generate knowledge from where there was no knowledge before. So let's say we can find a move 37. We can have a game of chess with all the knowledge that we have about chess, and then have a machine train to play that game, and then the machine comes up with something that we've never thought about before. Doesn't that mean there is an a priori? There is some ground truth of how to play this game that we're not even familiar with. So all we're doing is we're scratching the surface of truth, one experiment at a time, one machine at a time, one AI at a time. So what the difference is between traditional old-fashioned experimentalism and Popperian science, which is we have, the hypothesis, and then we either prove it or don't prove it and things like that, or he didn't use the word prove, he used the word falsify, or falsify, say, okay, this is wrong, and if I can't show that it's wrong, then it's right, until somebody comes up with a better theory, and then proves the theory that was considered right wrong. So this is the same, this new paradigm in science that I think is being propelled here in robotics, and that Ken Goldberg is mentioning in his talk. This new paradigm of science, it just means we're doing the same thing much faster. I mean, that's kind of where I stand in this conversation. But what it means for embodied intelligence in particular is that we have a chance to get to know nature much better now. But what we have to do is we have to get better at observing nature. So we really have to be able to observe nature. On the observation side, we don't have other options. Like, we have to be able to observe nature and represent it, ideally in simulation, so we can then have much better trajectories towards solving problems, whether it's doing surgery, or whether it's driving a car, or whether it's cleaning a kitchen. And maybe, often there is no need to have better trajectories, and we can just sort of settle with the existing trajectories and train robots with existing trajectories. For example, what Tesla did with the full self-drive 12.4, I believe it is now, no, 12.3, excuse me. 12.3 is based on imitation driving. So it's not superhuman. It just drives like humans. It's good enough. It drives. I don't have to drive. So it takes away my driving, which is a lot of effort and things like that. But there is a time when we can have superhuman driving, which will eventually reduce accidents and cost in general, cost to society of transport, which is great. So to summarize, Ken Goldberg's presentation is a great presentation, because I think what a true intellectual does to me is he makes me work. He makes me think. That's the fundamental idea about a true, interesting, inspiring intellectual. Whether it's an artist, whether it's a professor, whether it's an athlete like Valentina Shevchenko is an MMA fighter, and her technique, particularly in kickboxing, is so inspiring that it makes me want to go to the gym and train. that's, to me, that's a true artist. That's a true proficient. That's true proficiency. And it's not all like I'm not inspired by golf or tennis. I'm not interested in those games, but sometimes I am, like in fighting or in surfing. Callie Slater makes me want to go surf. So and nothing wrong with the sports that I'm not interested in. I'm just not interested in personally, and so on and so forth. But anyway, they inspire. The goats inspire you, and that's what's great. So in terms of scientists, there are people, Sergey Levin, Sijindra Malik, Petra Bilic. It's really the UC Berkeley robotics crowd really is special. Let me say that they're really special. They're onto something. I truly believe that they have this transcendental power that they think beyond the obvious, which is absolutely inspiring to me. So Ken is asking the question, is data enough? And Jitendra recently at his talk spoke about the convergence of engineering, old-fashioned engineering, control theory, and data-driven models. I believe that we should follow the idea of the OpenAI researchers that I met recently. They said, look, the more general the model, the less constraining the model, and the more data, the better the success. So the less constraining we have in the model, in other words, the less engineering, the less physics, the less of anything we have, and the more data, and the better. Now we have to think the art, I think the human ingenuity is not in coming up with better physics. It's coming up with better models, and it's coming up with better data pipelines, and it's coming up with better, AI infrastructure for learning, better GPUs, faster GPUs, more flexible software like CUDA or other software applications. Like, we're entering the area of multimodal transformer architecture, so we have to be able to represent different types of data, three-dimensional data. We want to represent physics. That implies more and more data and better and smarter data pipelines and algorithms. So there's really, the way I see the AI problem is really, threefold. One is we have to be able to represent reality as good as we can in machine-readable language. And we have to be able to represent what we see and also what we feel and how things behave in the real world. In other words, represent physics without using physics, ideally. Then we have to find ways to optimize trajectories. In other words, like reinforcement learning is one way to do this, probably the best way. So we optimize on the constraints, and then we have maybe techniques like Q-learning, where we have a certain action based on certain states, and then we derive policies from value functions. So if we take this action, we maximize the value of a reward function. But then the ingenuity here is really in designing those reward functions, even designing the Q-learning algorithms. How about we have a couple of actions? Let's say we do a summary of averaging out many actions instead of just action by action. So there's a lot of research in reinforcement learning, but I think that's the path to go. So again, represent reality, find ways to find optimal trajectories, and then third, once we have all that together, translate that into reality. So these things will happen in simulation. The first two, represent reality and find best trajectories, and then apply to the real world in terms of sim to real translation. So those three components, I think, are the future of robotics. They're also the future of science. And they're the future of philosophy, in a sense that we will find better ways to discuss a priori, to discuss truth, transcendental idealism by Kant, for example, which says that we represent our reality, that we understand what we call reality is nothing but an illusion. It's a modeling of the world that we understand, but it's not the real world. That is, in my opinion, exactly the way I see it. But there is more to learn, and we can use those machines and the AI to scratch more from the sort of lift the fog, if you will, and get closer to the a priori. I am a believer of that. I can't prove it, but I think robotics and AI are a way to prove that there is an a priori, that we are transcendental idealists, and that the best way to proceed is to actually to create machines that can iterate much faster than we can, so we can create knowledge much faster and at lower cost. Thank you.